rotational kinematics. In this section, we study the rotational motion without considering the torques. First, we go over some definitions. The first definition is arc length, which is represented by S. The arc length S is equal to radius R times theta. It's important to remember here that theta must be in radians. We cannot use degrees. The second definition is the average angular speed. The average angular speed is given by delta theta divided by delta t, where delta theta is equal to theta minus theta 0. Theta is the final angular position. Theta 0 is the initial angular position. And the arrow above omega represents that it's a vector. The bar represents that it's the average value. So this means the average angular speed. The quantity delta theta is called the angular displacement. It's the change in the angle. The units of the angular speed is radians per second. We can also write the average angular speed as theta minus theta 0 divided by delta t. The other definition is average angular acceleration, which is represented by alpha. So the average angular acceleration is given by delta omega over delta t. The units are radians per second squared. In general, there are two types of accelerations in a rotational motion. One is the centripetal acceleration that we learned previously, which is pointed towards the center. The other type of acceleration is called the tangential acceleration, which is tangent to the circle. These two accelerations are perpendicular to each other. The tangential acceleration at is given by radius times alpha. The centripetal acceleration AC is given by v squared over r. So the total acceleration, the net acceleration given by square root of at squared plus ac squared. Now we go over equations of rotational kinematics. These are the rotational version of equations of kinematics we learned in chapter 2. The equations are pretty similar. The difference here is the velocity is replaced by angular velocity. The displacement is replaced by angular displacement, and the acceleration is replaced by angular acceleration. Other than that, it's the same set of equations. The first equation is omega equals to omega 0 plus alpha t. Omega is the final angular velocity. Omega 0 is the initial angular velocity. Alpha is the angular acceleration. The second equation is theta equals to omega plus omega 0 over 2 times t. Theta is the angular displacement. Omega is the final angular velocity. Omega 0 is the initial angular velocity. T is time. Third equation is omega squared equals to omega 0 squared plus 2 alpha theta. And the fourth equation is theta equals to omega 0 t plus 1 half alpha times t squared. So these are the four equations that we normally use in problems. So now we go over some examples. Example 1. A circular disc of radius 8 centimeters is rotating at an angular speed of 12 radians per second. When t equals to 0 seconds, its angular speed is 15 radians per second. When t equals to 3 seconds. Question A. Find the angular acceleration of the disc. Question B. Find the net acceleration on a point at the outer edge of the disk at t equals to 3 seconds. Question C is what is the angular displacement of the disk from t equals to 0 to t equals to 3 seconds. Now first we write down what's given in the question. The initial angular velocity, is 12 radians per second. The final angular velocity is 15 radians per second. Time is 3 minus 0, which is 3 seconds. The first question was to find the angular acceleration. So the angular acceleration alpha equals to delta omega over delta t. Omega final is 15, omega initial is 12, so the change is 15 minus 12. Delta t is the time, which is 3. So 15 minus 12 divided by 3, so we get 1 radian per second squared. So that's the angular acceleration. The second question was to find the net acceleration. So to find the net acceleration, we need two accelerations, AC, centripetal acceleration, and AT, tangential acceleration. So AC is given by v squared over r. But v is not given in the question, but we can find v using the formula v equals to radius times omega. So AC equals to radius times omega squared divided by r. So that's r times omega squared. So AC is r times omega squared. So that's 0.08 times 15 squared, because we need to convert the radius into meters. So that's why it's 0.08. So it's 18 meters per second squared. So that's the centripetal acceleration. The tangential acceleration is radius times alpha. Radius is 0.08, alpha angular acceleration, which is 1 radians per second squared. So the tangential acceleration becomes 0.08 meters per second squared. So the net acceleration is square root of AC squared plus AT squared, which is square root of 18 squared plus 0.08 squared. So the answer is 18.002 meters per second squared. Part C, the angular displacement theta is omega 0 plus omega over 2 times t. 12 plus 15 over 2 times 3, so that's 40.5 radians. Example 2, a motor starts from rest and accelerates till it reaches its operating angular speed 2000 rpm. The motor takes 2 minutes to reach this speed. Find the angular acceleration and the angular displacement of the motor. So again, the formula angular acceleration alpha delta omega over delta t, which is final angular speed minus initial angular speed divided by 2. The final angular speed is 2000 rpm minus 0 over 2. The units are revolutions per minute divided by minutes, so revolutions per minute squared. We need to convert that to radians per second squared. To do that, we need to first convert revolutions into radians. That can be done by multiplying revolutions by 2 pi. So this becomes radians. Then we have minute squared. To convert minute squared into second squared, we need to divide that by 60 times 60. So the answer is 1.74 radians per second squared. The second part is angular displacement. Can be obtained using this formula omega plus omega 0 over 2 times t. So it's 0 plus 2000 over 2. That's in revolutions per minute or rpm. Then the time is 2 minutes, so you multiply that by 2. So minutes cancel here. The answer is 2000 revolutions. To convert that into radians, we multiply that by 2 pi. So it's 2000 times 2 pi radians. So the answer is 12,560 radians. This is the third example. A pulley system is used to lift a heavy weight as shown in the diagram. So we have a larger pulley here and a smaller pulley, and the larger pulley has a rope wrapped around it, and this rope is pulled at a constant speed of 0.5 meters per second. So when you pull this rope down, the weight moves upward with some speed. So the question says the rope wrapped around the larger pulley is pulled down at 0.5 meters per second. Find the speed of the weight. The radius 1, that's the radius of the smaller pulley, is 10 centimeters. Radius 2, which is the radius of the larger pulley, is 25 centimeters. So we need to find the speed that the weight is moving upward. So in the pulley system, both pulleys have the same angular speed. But if you take a point at the edge of the pulley, the velocity on the larger pulley is different than the velocity on the smaller pulley, because the reason is velocity is equal to radius times the angular speed. So, but the angular speed, the angle that they move through, is the same for both pulleys. So we can write the angular speed for both pulleys and we can equate them. For the smaller pulley, angular speed is its speed v1 divided by radius 1. For the larger pulley, the angular speed is its speed v2 divided by radius 2. Here what we mean by v1 and v2 is the speed that a point at the outer edge is moving, which is the same speed that is being pulled here, and that would be the same speed that the weight is moving upward. By solving the equation for v1, we get v1 equals to v2 times r1 divided by r2. So it's 0.5 times 10 divided by 25, which is 0.2 meters per second. So when you pull this rope at 0.5 meters per second, the weight moves upward at 0.2 meters per second.